In the previous video, we were introduced to a two-step model which described the reaction between an enzyme and a substrate to form an enzyme-substrate complex, and that complex then being converted to an enzyme plus products. In this video, we're going to explore this mechanism in a little more detail and arrive at a new equation that allows us to fully understand the kinetics that enzymes undergo. Okay, so as a reminder, we said that this second step here, K2, was the slow step, the rate determining step, meaning that the overall rate of this reaction is equal to K2 times the concentration of the enzyme substrate complex. Okay, so a few important things that I want us to keep in mind as we go through this discussion. Okay, so one of the really important points is that the total concentration of our enzyme, so I'm going to say E total here. So the total concentration of the enzyme at any point is equal to the concentration of free enzyme, which we see here in our mechanisms, plus the concentration of the enzyme substrate complex, which is observed here. So the total enzyme concentration is equal to the sum of all the different forms that are present. And in this mechanism, we only have free enzyme or the enzyme substrate complex. Okay, another really important thing to keep in mind is that the maximum rate, so we're going to call this Vmax. So the maximum rate of a reaction is going to occur when the concentration of the enzyme substrate complex has reached a maximum. Okay, so we know according to this rate law that the rate, in this case Vmax, is equal to K2 times the concentration of enzyme substrate complex that's been maximized. Okay, and if we kind of apply what we see here, right, so if we apply this situation, then the maximum concentration of the enzyme substrate complex is going to occur when the concentration of the enzyme is essentially zero. So the maximum rate is going to end up being when all of the enzyme is tied up as an enzyme substrate complex. And the third thing that we should really focus in on here is that this equilibrium, right, so this first step, converting enzyme and substrate to an enzyme substrate complex, is an equilibrium reaction. So point number 3 here is that we have this equilibrium. So enzyme plus substrate goes to the enzyme substrate complex is governed by an equilibrium constant, so capital K. So now that we have these 3 points established, I'm going to go ahead and introduce the Michelis-Menten equation. Okay, this equation is V naught, so the initial velocity, is equal to Vmax times the concentration of substrate divided by Km plus the concentration of substrate. Okay, so in this equation, we see some very familiar things, right? So we see substrate concentration. So concentration of S is equal to the substrate concentration. And this should be fairly self-explanatory, right? So just like when we're dealing with the rate of traditional reactions, we know the concentration of reactants are important. And correspondingly with enzymes, the concentration of substrate, which is one of the reactants, is important. Okay? V naught is the initial rate, so this is the rate of the reaction. Vmax, as we've already talked about, is the maximal rate. And as we've seen before, this occurs when 100% of the enzyme is present as an enzyme substrate complex. And Km is the last piece here. We call this our Michaelis constant. And what you'll note is that Km is a capital K, so it's an equilibrium constant. And specifically, this equilibrium constant deals with the equilibrium of enzyme substrate complex dissociating into an enzyme plus a substrate. So what you'll note is this is the reverse of the original enzyme mechanism we talked about, where we have enzyme plus substrate becoming the complex, right? So up here we saw that we have this equilibrium where we have an enzyme plus a substrate becoming the complex. So the Michaelis constant describes the reverse of this, where we have the enzyme substrate complex decomposing to form an enzyme plus a substrate. All right, so Km then is equal to the concentration of enzyme, the concentration of substrate, divided by the concentration of that complex. And if we think about this in terms of units, all three of these terms are concentration units. So the units of the Michaelis constant will be molar. It'll have concentration units. The most important thing about the Michaelis constant is that it tells us about the strength of interaction between the enzyme and the substrate. So we're dealing with the strength of the interaction. Okay, since this is a dissociation constant, we're looking at the dissociation of the complex. The higher the value, so large Km's mean low affinity. So there's a weak interaction between the enzyme and the substrate. The larger the Michaelis constant is, the weaker the interaction is between the enzyme and the substrate. But really small Michaelis constants, right, so really small Km values, mean we have a high affinity. So the enzyme binds to the substrate really tightly. Okay, so for example, if we had 1 micromolar Km versus 1 millimolar Km, since 1 micromolar is a smaller number, this would be the more high affinity interaction between an enzyme and a substrate. Alright, so let's recap. We said that the Michelis-Menten equation is V0 equals Vmax times the concentration of substrate divided by Km plus the concentration of substrate. Within this equation, we have some really important pieces of information. V0 is measurable. This is experimentally determinable. It depends on the concentration of substrate. So as you increase the concentration of substrate, you would increase the rate of the reaction to increase as well. Okay? Vmax is the maximal rate. So this occurs when 100% of the enzyme is present in the form of the enzyme substrate complex. And Km is the Michaelis constant, and it describes the affinity between the enzyme and the substrate. In the next video, we're going to explore this equation graphically, and we're going to see that we can make some very logical predictions about how the enzyme is behaving as we start changing these variables.